Hello and welcome. In this video, we'll be discussing how we can implement ANOVA for simple linear regression using R. To start this video, I'll be pulling in a bunch of stuff that we've already calculated, the data, of course, my notation, just listing the variables X and Y instead of marketing and profit so that I can quickly access these variables in the calculation, X bar and Y bar, the means of each of the variables, the simple linear regression model, the coefficients, and Y hat. So all of this stuff I'm going to be bringing in to start out my work in the ANOVA. Now, for the ANOVA, if you remember the ANOVA pieces were actually relatively straightforward in terms of their calculation once we're using R. So for R, essentially, we took the sum of squares total, which is Y minus Y bar. We raised these to the second power, and then we added all these up, and this was the sum of squares total. And that's it. That's what we do. Take all the y's, subtract the means from it, raise all those values to the second power, and then add them all up, and that's the sum of squares total. The sum of squares regression was very similar. We took Y hat minus Y bar, all these values, raised them to the second power, wrap them in parentheses, raise it to the second power, and then add it all up. And that is my sum of squares for regression. And then sum of squared error, very similar. SSE, we have our Y minus Y hat. We take each of these and we raise them to the second power, add them all up. And you'll see I'm doing a lot of copying and pasting here, of course. No need to reinvent the wheel. So I have my sum of squares error, my sum of squares regression, and sum of squares total that these should both add to. And that's my big starting place, y'all, for ANOVA. Yeah, that's the really, really hard part. So this is a lot cleaner, at least to me, than the actual ANOVA was. ANOVA for regression just feels a little bit cleaner and easier. In any case, let's go on and figure out the rest of this. So I'm going to need P, the number of independent variables. That's going to be 1. N is the sample size. And again, just the length of X or Y will do to find that quickly. My degrees of freedom for regression is P. My degrees of freedom for the error is N minus P minus 1. My degrees of freedom total is N minus 1. Now that I have the degrees of freedom, I can go on and calculate the mean squares. The mean squared regression is the sum of squares for regression over the degrees of freedom for regression. And the mean squared error is the sum of squared error over the degrees of freedom for the error. So I'm just kind of plugging along. I'm not really making things up. I will say this is, again, one of the reasons I really like making variables. So if I have SSR, this quantity saved is the sum of squares of regression. Now I don't have to think about, okay, the mean squares of regression is 5.18, blah. I don't have to think about all the numbers. I just think about the concept. The concept is SSR over DFR. Okay, well, I saved a number called SSR that has the appropriate quantity. I saved a number called DFR that has the appropriate quantity. MSR is just SSR over DFR. That's it. All right. Moving on here, we have, let's see, F is going to be the MSR, mean squares regression over the mean squares error. That's my F ratio. And this F just being my test statistic. So once I'm here, I have my test statistic and I can go on and look at my critical value. This is from the F distribution, QF. I give it my alpha level, 0.05, let's say. I can't actually remember what it was here. Degrees of freedom 1 is the degrees of freedom from the numerator, so degrees of freedom regression. Degrees of freedom 2 is the degrees of freedom from the denominator, degrees of freedom error. And again, these are just numbers. So if you prefer just typing in the numbers, just type in 1 and 5 in those places. Lower dot tail equals false. Fantastic. So this is my cutoff. My test statistic, F, is not greater than my cutoff, so we don't have a significant relationship between marketing and profit. Not enough evidence to determine one. To do the p-value here, I would do the, let's see, PF, give it my test statistic, degrees of freedom 1 equals DF regression, degrees of freedom 2 is the degrees of freedom error. And again, I like having the variables name this because I can just do it conceptually. Yeah, the numerator degrees of freedom is the degrees of freedom regression. I don't have to think about what actually is that number. Lower tail equals false. Non-numeric argument. Okay, it looks like I messed something up here. Degrees of freedom regression. Well, so let's troubleshoot this. I won't redo this one. I'll just look at it. So TS. So TS. Well, TS evidently is some fancy command that does something crazy, and I have no idea what that is. So that's not what I wanted TS to be. I didn't actually want to put TS in this case. I wanted to put F. So remember, I was using F as the variable of my test statistic. So that was an issue. Here I get my p-value is 0.1126. Remember, this is actually the identical p-value we got when we tested the slope in the previous video. So that's always a good sign. Yeah, and that's my ANOVA in R, and yeah, I did a little error checking at the end here, but pretty simple and straightforward. This might be the shortest video ever. Oh, we got to do the built-in. All right, built-in commands. This isn't going to take too much longer. Tests. Essentially, I take that simple linear regression model that I built in the kind of the precursor here, LM, profit, squiggle marketing, and I saved it as the variable SLR mod. I just wrapped that in an ANOVA, ANOVA open parentheses, put in my SLR mod, and then I get my simple linear regression model. I've got my sum of squares regression, sum of squares error, I got my degrees of freedom regression error, my mean squares regression and error. I've got all these pieces already built into that table, so it makes it really, really easy. My p-value matches the p-value that I found earlier too. Yeah, so nice, easy, straightforward. Again, if you have raw data, use the built-in commands. They're way quicker. They're probably more accurate too. If you need the specific pieces, you'll kind of have to do it the longhand way, and that's fine too. Even doing it the longhand way, depending on how you're approaching it, doesn't take too much time, if I can say that. I guess it depends on who you are, but hopefully you'll find this to be a lot easier than actually manually calculating this stuff. So for instance, when I'm doing y minus y bar squared and then adding them all up, hopefully figuring this out and doing it here is just a lot easier. Again, each of the y values minus each of those minus y bar, taking those differences, squaring each of them, and then adding them all up. Hopefully that makes life a little bit easier for you. So in any case, this has been how do we do ANOVA for regression in R. We kind of did the by hand way first, and that went pretty quick. And then we did the built-in test, and that was super quick. So yeah, maybe our shortest video ever. Anyway, I appreciate you sticking with me through this one, as little as it was. And I will look forward to seeing you in the next video.